All right, so the example that we're going to be talking about is number 13 in chapter 2. It's on page 32 if you want to go back and look at it. So if you go back and watch this video or anything like that and you want to actually look at it, you can. So this is a question about somebody who has a coin and they're going to flip it. Okay, so maybe they're doing like the heads or tails thing, but they're going to flip it and then they are going to catch it at the same height. Okay. Let's see. Where's the full? There we go. So the coin is flipped upwards with an initial velocity of 5 meters per second. We don't really know how high it goes or anything like that, but we do know that it is caught at the same height, and we want to know how long it is in the air. Okay? Anybody remember doing problems kind of like this freshman year? Vaguely? Okay. So there's several things I want to talk about with this. So let's start by drawing out our picture for our problem. So we have a coin. Here's our coin. And we are going to flip it upwards with an initial velocity of 5.0 meters per second. And this marker is failing epically. All right. Let's see what we can do with that. The camera's not focusing again. We'll see if we can. Still not focusing. All right, well, that could make reading the notes from the live stream interesting. Oh, there we go. Okay, cool. Sorry about that. So we have the coin. It's being thrown up with an initial velocity of 5 meters per second. Okay? That's all that the problem tells us. Okay? So we need to add some information just from knowledge that we have. What do you think is going to be important information?
Force of gravity.
Not force.
Acceleration.
The acceleration of gravity. Okay? The acceleration of gravity is what's going to be slowing this coin down as it goes upward and then speeding it back up as it comes back down. Right? So we probably need to know that. What is the acceleration of gravity? 9.81. So our acceleration is 9.81 meters per second squared. Have I written it down 100% correctly?
I'm guessing not.
No. What is missing?
Isn't it negative?
Okay, we need to make something negative. Okay? Our velocity is currently going upward, and our acceleration coming from gravity. Acceleration from gravity is always going to pull it downward, right? These are in opposite directions, so we need to use a negative sign to show that they are actually opposites. Okay? Which one do we want to make negative? It doesn't actually matter.
Gravity.
Gravity? Okay. So we have a negative 9.81. Good?
Does it matter which one you have negative or positive?
No. Just as long as you are consistent. I did just say that.
Okay, that's what I thought. But...
Yeah. It does not matter. Just pick one, stick with that direction being negative. Okay? It's just like our vector addition where we say one direction is negative. Okay? So, what we are ultimately looking for is the time it takes to come back to the same height. So we're looking for time. Okay? So, any ideas of what we might want to do next?
How high is it?
Maybe. We might need to know a height, so we can look here at a height. That might be something we might want to know. Other things we might want to know.
it started.
Okay, where it started, that's definitely a good thing to define. In this case, because we can define it, let's call it 0. That'll make our life a lot easier. Okay, so we're going to call this 0 meters. Other things we need to know.
How long it takes to get to a certain point?
Okay, so our time to the top is going to be up here. Other things you might want to know? No? You guys can't think of anything right now? All right. So we've got some things defined, and it's always better to define more things than less things. So we may not use all of these variables. There's ways that we can solve it using the time to the top. There's ways we can solve it using the total time. There's several different ways we can actually solve this problem. So once you've kind of drawn your picture and labeled some stuff, try thinking about what equations you might want to use. Okay? Are there any ideas for equations we might want to use? Hint, they're probably one of the equations we talked about on Friday.
Is there a specific name though? I'm guessing there is.
For the equations,
Yeah.
there's the position equation and the velocity equation, but that's, I mean, they don't have like it's not like, I don't know, Newton's laws have names. It's not like that. At least I've never heard names for them. Any ideas on what equations might be good ones to look at least?
The 1/2 times a t squared.
Yep, that's a good one to start with. We've got x equals 1/2 at squared plus v naught t plus x naught. So we've got that one to start with. Okay. Any other ones we want to look at that might be useful? We might even have to use multiple equations, you never know.
You can use the velocity equation.
Okay. So we've got v equals at plus v naught.
How many? Which is like v minus v naught over a.
So we solved this one 4 times. We've got t equals v minus v naught over a. Okay. This one's looking kind of promising because we are looking for time, right? So that might be helpful. I will tell you guys right now that if you can use, I guess this is the same as this equation really, but if you can use this equation to find time, use it. If you can't, a lot of times you're going to have to use like quadratic formula and stuff to solve this one because it doesn't factor out nicely most of the time. So just be aware of that. If you can use a velocity equation to solve for time, I would highly recommend it. Okay? Cool. Just kind of an overall blanket helpful hint, hopefully. So we can actually solve it with one of these equations up here. Okay? Which one do you think is probably going to be the most likely?
The third one.
The third one? Yeah. Definitely a reasonable guess. Okay? So we're looking for time. Good start, right? Solve for time already. We know our acceleration because we're talking about a free fall problem. We're always going to know our acceleration. Okay? We know our initial velocity, right? Looking good so far. Okay? We got the 5 meters per second there. What about our final velocity? Do we know anything about our final velocity?
It's going to be 0
Where is it 0?
at the end.
Here?
Yeah.
Well, this is before we catch it. So like right before it hits our hand. Okay? So it's not going to be 0 right before it hits our hand.
At the top.
Okay? It is actually going to be 0 when it gets to the very, very top. Okay? Or not B. Okay, so we have a velocity there. Is that particularly helpful? Because we're looking for our whole time. So we can find the time it takes to go from here to here, right? So that's not unhelpful. But is that going to be particularly helpful? Okay, I'm seeing some no's. This is where we can actually use some, I guess, approximations, but really, really good approximations. Okay? Is the motion of it going up really that much different than the motion of it going down? No. Right? It looks very similar going up, and then it kind of has the mirror image coming back down, right? Same shape to the path. It goes up and slows down as it goes up, but then speeds up as it comes back down, right? Yeah? This is actually what we call a symmetric path, okay? That means that it's the same on both sides. Yes, you're going in a different direction, but the amount of time it takes you to get to the top is actually the same as the amount of time it takes you to get back to that same height. And the only reason this works is because you have a constant acceleration the entire time. Does that kind of make sense? So the time to the top is equal to the time it takes for it to fall back down again. Okay, so this time to the top is actually really helpful because it's half of our total time. Does that make sense? Okay. There's actually another way that we can solve this, and we're going to go back and talk about this in a second. But let's solve it this way first. Okay? Good? All right. So, to use this equation to solve it this way, we're actually going to find our time to the top, not our total time. Okay? So, our time to the top, which we call TT in this case. Side note, this is generally how you would designate total time, but in this case, we're using it as time to the top. Cool? So maybe I'll put time to the top. So we have our final velocity, which is 5 meters per second, minus our initial, which, or final, sorry. No, wait, I got this backwards, don't I? Sorry. So our initial velocity is the 5 meters per second. Marker really is not working very well anymore. All right, 5 meters per second. And then we have our initial velocity, our final velocity, sorry, which is 0 meters per second. Good? Everybody see where we got all that? Okay. Then we have our acceleration, which is negative 9.1, or 9.81, sorry. Okay, so we've got negative 9.81 meters per second squared on the bottom. Good? All right, what do we get when we take 5 divided by 9.81? Because our negative signs are going to cancel out.
0.516.
Okay? And units-wise, we have meters per second divided by meters per second squared. The meters will cancel out, and 1 of the seconds will cancel out. Okay? Since this flips over, we do get seconds where it should be. Cool? Yeah? So we get 0.51 seconds. Now, this is not the whole time. This is only half the time. So we do need to go back and multiply this by 2. Right? All right. So when we multiply this by 2, we get 1.02. Okay. Everybody good? Yeah? Okay. So this problem is not particularly hard when we actually get to the math portion of it, right? But we have to use our knowledge about the situation to actually give us some of our values. Everybody see that? Okay. So there is actually another way that we can solve this. Okay? Also, if we simplify this down to get the time, we can actually just say that it's 2v over a. That does actually, no, sorry, negative 2v over a. Sorry. So this is exactly what we've done here, and I kind of want to show you how that's the case, right? So here, right, we have negative v. And if we are looking at this as we're looking at the time to the top, that top value is always going to be 0 every single time, because that's essentially how we've defined it, right? So that top value is always 0, so we can just kind of get rid of it, okay? So here, we've got our negative v, and that's here. We've got our acceleration on the bottom, and then we multiplied it by 2, right? Yeah? So this is going to be your total time. It's kind of a shortcut equation. It only works if you catch it at the same height, okay? Okay, so this is going to be one of our first equations where we have that caveat. It only works in this case. This equation works all the time. As long as you have that initial and final velocity and you have some sort of acceleration, it works every time. Good? This one and this one work all the time. There is no situation where they don't work. This one is a special case where we are assuming that top velocity is 0 and we are catching it at the same height. So we're assuming that it is a symmetric path and we're catching it at the same height. Good? This also really only works because we are assuming there is no air resistance. If we were like in a wind tunnel or something, like one of those indoor skydiving things, and we tossed something upward, we're not going to have a symmetric path anymore, right? Because we now have a huge force pushing it upwards. It's going to go upward a lot faster. It might even not come back to the same height. It might stay up there floating, right? Yeah? So this is assuming that we are in free fall. Free fall says that there is no air resistance. Cool? All right. Ignoring air resistance makes this problem a lot easier. It's also not a bad assumption, because for the speeds that we're talking about with something like this, just going like that, it's not going that fast. It's also a fairly aerodynamic shape. Air resistance is going to have a very, very small effect on it. Cool? Okay. Air resistance, fun fact, is not a linear thing. So if you have very low speeds, like under 10 miles an hour, you're really not going to have a whole lot of air resistance. That is assuming there's no wind, because wind would increase your relative velocity, which would mean you're not going 10 miles an hour anymore. Good? Okay. Once you get to about 50 miles an hour is where you get out of the range where it's linear. So if you guys are actually on Route K and you're speeding up on Route K, if you have your windows down, you'll notice that when you reach 50, it gets a lot louder. Or right around 45, 50, it suddenly gets a lot louder. That's because your air resistance is increasing, and you can actually hear that quite a bit. Cool? Kind of makes sense? Okay. If you've ever done that thing where you stick your hand out the window and you go like that through the air, you will notice a big difference once you get to like 45. Cool? All right. So, anyways, that was a long tangent to say that free fall is a really good approximation for this situation. Good? Okay. All right, the other way we can think about this, and fun fact, we're going to get this exact same equation out of it. Okay? The other way we can think about it is we can go back to the fact that this problem is symmetric. Okay? it starts at 5 meters per second, it goes up, it stops, it then has the same acceleration speeding it back up, right? So what speed is it going to have down here? Symmetric. Same on both sides. It's going to have 5 meters per second, but the difference is going to be the direction. So your direction is now downward instead of upward. Does that make sense? Okay, so here we have a velocity of 5 meters per second. Okay, this we would write as negative 5 meters per second. And so then we can come back and we can actually put these values into this equation here. And this time, rather than getting half of our time, we're going to get the total time, right? So it goes up, it comes back down. So our total time in this case is going to be our final velocity, which is negative 5 meters per second, minus 5 meters per second. Okay, I forgot the points here. There we go. And then divided by our acceleration, which is negative 9.81 meters per second squared. Okay? Notice, those are the same, right? So once again, this numerator is 2 times the negative of our initial velocity, right? Yeah? So we get that same negative 2v, right? I guess I should put the v not there. Negative 2 times our initial velocity divided by our acceleration. Good? All right, so we get the same equation out no matter which way we do it, which is what happens a lot of times in physics, because we can approach a problem several different ways and still get the same thing. Okay? Good? That's actually why a lot of times on your homework, I always want you to show your work, and I actually go through and grade your work, because generally there's at least 2 different ways that you can validly do it, if not many more. Okay? Cool? So I want to know that you're doing it in a correct way and not just copying an answer from the book or something. So that's why I do go and grade your work. I don't actually generally use the answer key from the book because the answer key from the book says to do it only one way. And like I said, here we've got 2 perfectly valid ways to get to the same equation, right? So you can do it either way. And I just want to make sure that you get to the answer in a reasonable fashion. Cool?
Are we gonna need our book for more?
I was not planning on, I'm not planning on you needing it for tomorrow, no. I actually hadn't thought about what I was going to do for your assignment tomorrow. Glad you said something. It's not going to be hard.
Okay, good.
It's probably going to be a problem something like this, and I'll have you take a picture of your work.
Good.
So it's not going to be anything too hard. Honestly, what it might be is something similar, but instead of stopping at the same height, talking about what happens when it goes below where it started or somewhere else. Okay? So, how much time? We have till 17, right? Okay. I guess we can start a problem like that. So, like I said, this only works if you catch it at the same height. So if we have something where we flip a coin and then we catch it, I don't know, down here. So maybe, I don't know, a foot below where we threw it from. These equations are no longer valid. That's not going to give us our total time. We have to kind of go back and figure out how it's going to be different. Okay? All right. So, let's see. Trying to debate because I didn't think we'd get through this fast. So, trying to debate if I want to ask you guys for position or time or ending velocity. Let's try time, because time generally does work pretty well. All right, we're going to go back to our equations that are true all the time. Okay? Now, if we have a situation where we are no longer stopping at the same height, our assumption that this is symmetric no longer holds, right? Because we blatantly can see it's not symmetric anymore. It's going to go up and it's going to fall farther than the distance it went up, right? So there are several things that we can look at with this. We can still say that the velocity at the top is still going to be 0. That is still valid. We never said anything about it having to be symmetric before we said this. Okay? So your velocity at this top is still going to be 0. Good? Okay. For any problem where it ends below here, you are always going to be doing some sort of combination of maybe finding the height that it went up. Okay? And then finding the height or the distance it fell. So you can see how high it was above the ground down here. Or you're going to be finding the velocity that it hit the ground. Okay, so maybe you know the height from here down. Okay, and you're going to be finding the velocity when it hit the ground. Or you're going to figure out how long it's in the air. Okay, got it? Those are the kind of problems that generally go with something like this. In general, a problem that says, hey, you end at a velocity of negative 10 meters per second is going to be easier because you get to use this equation. Okay? However, if it says you are dropping a ball off a cliff that's 12 meters tall, you have to use this equation. Okay? And anytime you can use the simpler one, you should go for it. We're going to start with the one where you can use the simpler one, okay? Because we don't have a whole lot of time left. So in this case, most of the time, the easiest way to go about this is if you have both velocities, you can do just like we did in the second time. Where we say it's going up at 5 meters per second, it's coming down at negative 10 meters per second. What's the time it would take to go from those with that acceleration? Okay, so this problem's pretty straightforward. We just use this equation once again. Our final velocity is negative 10. Our initial velocity is positive 5, but it's subtracted. It's divided by 9.81. What do we get?
2.55.
2.55. So a problem like this is not particularly hard, right? We can get to this answer pretty quickly. Nothing too crazy going on here, okay? When it starts to get hard is when you are asked to find, say, the height of this cliff, okay? You are now tossing a coin upward, but you only want to find the height here. Okay? Does that kind of make sense? In a situation like that, what you really want is the time from here to here. And so if you can find the time here, and then treat this as a separate free fall problem, that's generally the easiest thing to do. So, have a good day, guys. I will make an assignment for you for tomorrow. It'll probably have something to do with free fall like this. Have a good day.
Yeah.